Hello, everyone. Intergraph Government Solutions and Carahsoft Technology would like to welcome you to our Intergraph webcast. Before we get started, I would like to go over a few housekeeping items. Audio can be heard today through your computer speakers or entering your number in the dial-out option on your screen. All of your lines have been muted to reduce background noise. We hope you ask questions using the Q&A tab on the left side of your screen. We will do our best to answer all of your questions at the end of the presentation. If for some reason we do not get to your questions, our team will certainly follow up with you offline. Just to tell you a little bit about Carahsoft, we are a trusted government IT solutions provider delivering software and support solutions to federal, state, and local government agencies. Carahsoft maintains dedicated teams to support sales and marketing for all of its vendors, including Adobe, VMware, and Symantec. Our contact information will be at the end of the presentation, so please don't hesitate to call or email us for any of your needs. This webcast is being recorded, and a copy of the presentation will be emailed to you. At this time, I would like to introduce our speakers for today. Rob Mott, Vice President of Geospatial Solutions from Intergraph, and Steve Duplessis, Product Line Executive for Intergraph. Rob will start us off for today. Rob, the floor is all yours.
Great. Thanks, Erin. First, I would like to let the folks know that the ERDAS Imagine is a product that is brought to market by Intergraph Corporation, which is part of a larger entity, Hexagon AB Group. And Hexagon actually includes Leica GeoSolutions as well. So as the next slide shows, we've got quite a range of technologies covering sensor collection all the way through processing, analysis, and visualization. So that brings a great team of experts to help our customers, our partners, solve their problems in dealing with LiDAR, any other types of remote sensing data, and a broad range of geospatial technologies and challenges. First, I'd like to just give a brief definition of LiDAR. According to Wikipedia, this is light detection and ranging, and it's using laser technologies to bounce off an object and record something back that is then represented in a data set. And there are a variety of different ways to collect LiDAR. The first and probably the most widely used are airborne-based sensors that are part of some light aircraft or even some rotary wing aircraft that are used to collect data as those aircraft move across the terrain. Terrestrial LiDAR, we may have a tripod-mounted system for surveying or even collecting information about the interior of a building. Additionally, mobile LiDAR is becoming a very popular mode to collect point cloud data as well. These sensor packs can be fitted on vehicles or even outfitted to handheld devices and used to collect a variety of types of information about the surrounding environment. Additionally, the ERDAS Imagine product set will allow artificially generated point clouds to be derived from stereo imagery, and that's a very powerful capability that will help round out the various mechanisms for collecting LiDAR. And so what does LiDAR look like? One tool I've used to explain this to my children at home is that you've got a pin art box here as shown by this graphic, and I push that against my hand. I have these individual pins, these lines, that then give me a physical representation of my hand. As the next graphic will show, when we have a digital version of that, as collected through a LiDAR system, we have a very rich, very robust depiction using billions, in some cases, of data points from these sensors that are then collected, processed, and turned into a digital reflection of our real-world environment. So what are a few applications? And there are quite a range of applications across many government organizations and across many private sector industries as well. One of the most important applications is in disaster response and recovery. The ability to collect LiDAR after a hurricane or an earthquake or some other catastrophic event is very powerful when used in a change detection workflow and very easily see differences in the environment before and after. Another set of applications relates to military operations and planning, and this may be urban environment modeling, which would support line of sight analysis, or cross-country mobility mapping as well. A third type of application is to survey archaeological sites. LiDAR's ability to penetrate tree canopies and give a bare earth representation is a very powerful, very important method to collect information and visualize areas that are unseen or in some cases inaccessible by land. And a fourth example of an application is corridor mapping, whether it's a utilities application or a transportation application to see encroachments from tree cover into these areas is very important, very powerful, and it gives a very quick, very reliable method to understand how changes in the environment are affecting the ability to provide utility services or transportation services to the citizens. So what I'd like to do now is turn it over to my colleague Steve Duplessis to provide a brief demonstration of some of the capabilities of ERDAS Imagine as it handles LiDAR data sets. Steve, over to you.
Thanks, Rob. So as Rob explained, I'm just going to give a brief demonstration in 15 minutes. I'm going to try to show you as much as I can of our little LiDAR tool, and I'll barely be scratching the surface. But let me start off with a little bit of a forestry type application. So what I've just dragged a LAS file into the viewer, and this piece of LiDAR data is kind of neat. The Forest Service uses it for illustrating the different types of information you can get from LiDAR. And so one of the first things you'll notice when I open a LiDAR data set, I get the new LiDAR or the point cloud tab, and this gives me all the tools for working with point data in Imagine. So I've got a number of file-to-file types of tools over here. For example, RGB encoding, and I can actually take a data set and encode my point cloud with it. And the name is a bit of a misnomer. It sort of implies that we're giving it a red, green, blue color palette, like a true color palette. But in reality, we can actually encode this point cloud with just about anything. So if we, for example, do an NDVI, we can encode the points with that NDVI value. Or if we do some kind of other analysis, we can actually encode the points. So this is, once we run that, we get a file that looks like this. So you can see a very sort of photorealistic, and if I increase the point size, you fill in some of the gaps that are present. Now you can really get a better feel for this area. We've got some clear cuts, we've got some thinned areas, and we've got some denser forests. And one of the neat things about having LiDAR capabilities in ERDAS Imagine is the fact that we can do all this kind of analysis that's typical remote sensing kind of forestry work or whatever you're doing, and we can combine it with now LiDAR analysis. So let me just give you a quick view of what we can do. For example, we can maybe open up a second viewer here. Open another 2D view, and in here I'm going to open up a raster layer. And then I can link this raster layer to my point cloud layer, so I can link the views and equalize the scales. Now wherever I move around, the two data sets are now linked, and we can see that data set inside there. So now I can do analysis on here. I can see how it's influencing work on my point cloud layer. I can also do things in my point cloud, such as profiles. So for example, I might want to see what it looks like if I do a transect from this side of the data set to the other side. And here now I actually get 3 views of the data. So I've got my profile from the beginning to the end of this profile corridor, and then I get a view across this little purple box over here and a view down the box. Now this one probably doesn't make too much sense, but I can also roam along that corridor. So if I push the play button, I can start roaming. You see exactly where I am on that profile. At any point I can stop, make some measurements. So for example, if I wanted to know how tall some of these trees are, I can come in here, click on the top of the tree, and make a measurement, and I get all kinds of information about that tree, and I can even put some notes in over here. Like I said, I can also take my image here, which is all linked to this analysis, and start bringing in, do an NDVI, bring in that classification, maybe encode my point cloud. But I've got all the tools that I need to analyze my data in one single application. I can also, and excuse the size of my real estate here, but I might be able to pop this screen off. I can actually unpin this viewer, put it on a different monitor, and I can see exactly where my transect goes. I can see the trees in 3D, and I've got all this information to interpret my data. So let me move now to a much larger data set. So this one's quite small, but it illustrates quite a bit of the utility. So I'm going to switch that off, and I'm going to bring in a data set. So this particular data set that I'm adding to this view now is something I downloaded off the internet, and it's freely available, last data. You can find it all over the world. And typically it comes in tiles, and you can see over here is one of the tiles, and you can see the tile boundaries. And in fact, when I downloaded this data, this particular tile was corrupted, and it just failed to read. And I actually went back and downloaded it. But the question is, what if I'm trying to do an analysis of this area, and for whatever reason, there's missing data? Maybe the file is corrupted permanently, or maybe it was never flown, or for some other reason, I'm missing data. Well, we do have a capability, again, built into the Imagine user experience that allows me to fix that kind of problem. So now, our photogrammetry suite is part of ERDAS Imagine, and I can go over here, and I can just open up a photogrammetry project, and I can actually extract these point clouds, these very dense point clouds, and fill in any missing data. Because typically you're going to find that there's some stereo data or stereo coverage of area, or at least much more prevalent than you'll find for LiDAR data. So here's my photogrammetry project. I can go up here, put a base map in for some context. I can switch my terrain layers off, and you can see the footprints of all my photos. But more importantly, I can go up here to my new photogrammetry tab and say generate one of these dense point clouds. Now you're probably thinking, if you generate point clouds using photogrammetry, you're going to get a pretty poor DEM, and it's going to be nothing like LiDAR. And to be honest, nowadays that can be not further from the truth. And I'll show you an example. Some of the photogrammetric point clouds that we collect are actually far denser than point clouds that come from LiDAR. In fact, if we got 5 centimeter imagery, we can actually generate these very dense point clouds at a resolution of about 300 or 400 points per square meter. So this is a point cloud derived photogrammetrically. We can switch on the RGB, which is inherent in this type of data set. If I increase the point size a little bit and merge these points, you see it almost looks like an image. Again, very dense. This is 5 centimeter imagery, so it's generating about 350 to 380 points per square meter. And if I show in 3D, again, you can see a very detailed data set with a lot of terrain detail and 3D detail. You can even see vehicles and stuff parked on top of this little quarry bank over here. Okay, so if I wanted to fix my data set, if I had missing data, I can do that. And so let me go back, and we go back to my Yosemite data set. And so I filled in this little piece over here that was missing, which was actually this tile over here. And I actually happened to have some NAPE imagery of this area, and so I went ahead and I RGB encoded this particular data set. Now, I'm a bit of a skydiving enthusiast, and I've always thought it would be kind of cool to jump off Half Dome, which is located over here where there's missing points because of the steep cliff. And I thought, well, maybe I can actually use the software we developed to figure out where a good landing zone is. So I can, in my LiDAR data set, I can actually do all kinds of things, like I can bring over a little profile. I can see the shape of the valley if I wanted to extend this over the cliff and start making maybe some measurements of exactly where I'm going to land. So here you can see Half Dome. Let me just switch off this up and down view. And I can go in here and start making some measurements. So how long is the vertical fall? What's the angle down to the valley? How long is the valley? And you can see all of these measurements are being recorded down here. But to be honest, this is not enough information for me. I need to know about vegetation. I need to know about the rivers. So maybe if I built a spatial model and incorporated this as part of the information into a much larger process, I might get a better idea of where I can land. So I'm going to close this up, and I'm going to open up a new spatial model editor. So this is the new spatial modeler in ERDAS Imagine. And I'm going to bring in this model that I created. And so essentially what this does is it looks at that elevation model or that LiDAR data set. But what I did was I took the LiDAR data set, I ran a classification on it, I then filtered out the trees, so I've got a bare earth representation, and then I created a raster out of it. And that's actually the last file is the input to this. It converts it into a raster, which then finds out the slope. And I don't want to land on very steep slopes. I want to land on pretty flat ground. I've also included the land cover down here. That'll help me avoid trees. And then, of course, I want to stay away from the river. So I brought in a shapefile. I've made a buffer around it, and then I've put it to an output. And I can run this, and it'll go through and give me a quick preview of what this data is going to look like. And I can then determine exactly where I'm going to be landing. So those are the landing spots. In fact, let me just open up an image underneath it so you can see where these are. Switch that off. I'll open up my nape, and I'll open up the landing zones. Background transparent, and maybe put in a neat color over there. So there you can see my little landing zones all around the valley to do that. Now that's pretty cool, but it might be a bit expensive, or I might not have the expertise to build this kind of model to figure out where I'm going to land. So one of the things that we can do is we can take this expertise, wrap it up, and publish it as a web processing service. So I can put these inputs, and it can actually ask the user and find them on a web service and tell the user exactly what this model does. It's called a web processing service. It's an OGC standard. And so once I push this, it publishes it out, and let me show you what that looks like on the web client side of things. So this is our standard web client. I'm just going to quickly log in here. And once I've logged in, it's actually going to show me all the geoprocesses that have been published to this particular Apollo server. And I'll be able to execute those particular services. So over here in my General tab, I've got a change detection process that we created. And what this does is it actually takes a data set that is created from this point cloud and actually combined with 4 bands of imagery. So the data set is actually a 5-band image, and the 5th band is actually elevation, and the first 4 are the red, green, blue, and infrared. And we can use that data to do very sophisticated change detection, and including the height aspect as well. So when I click on this particular model, it actually goes out and says, well, if you're going to run that model, you're going to need this kind of data. And it searches the service for the particular data sets that match the requirement of the service. And so it tells me a little bit about this. And again, this is something I create when I'm building the process. It says what is the before raster data set. So this is actually the 2010 data set that I've got over here. And let me just add it to the map while I'm at it. And I'm going to set this one as the before data set. And I'm going to set this one as the after data set. So I put in my two data sets over there. And actually there's a new little suburb over here that's, or a little subdivision that's been put in, and a whole bunch of new houses have been built. So let's see if we can detect this using this web process that we developed. So define my area of interest, push execute. You can see that the model is now running on the server. You can see the progress meter up there. And when it's complete, I can actually look at the results online. So I can just select it, say show the results, and, add these to the map. And so what we've actually done is the model actually takes the results and color codes them by change in height. And then we also, because we've got 4 bands of imagery associated with this, we can actually differentiate between the change of height of buildings and the change of height of trees and other vegetation. So if somebody planted a tree versus somebody put up a new building, we'd be able to distinguish those two differences based on the fact that we have imagery and LiDAR data. And that actually concludes my demonstration, so I'm going to hand this back to Rob.
Great, thanks, Steve. That was a great way to end the demonstration. We did go through this rather quickly. We are working in a 30-minute format, and so this essentially is a brief glimpse into some of the powerful capabilities that ERDAS Imagine can provide. We're available to support further demonstrations online or in person, and in fact providing evaluation copies of our software for folks to take and use with their own data sets is something we recommend and we can support. I'd like to summarize a couple of the key benefits to really underscore what Steve was able to show us, that the ability to analyze LiDAR in an integrated environment is very powerful, that you're working with other types of data. You've got raster imagery, you've got mapping information, you've got other kinds of geospatial data collections, and to work with them in an integrated manner represents a much richer decision support environment. The ability to process and visualize very large data sets very quickly is absolutely important. As the amount of data that we collect and it becomes available increases and the size of these files increase, it's absolutely imperative that you're able to work very smoothly, very quickly, and not be hampered by things like file size. As Steve showed in the kickoff of a web processing service to perform change detection between 2 LiDAR data sets, that's very, very powerful to encapsulate and then access online. And that can be stood up in a public cloud, in a private cloud, accessed from a handheld. It might be a soldier in a field that wants to get the latest information about his urban environment before he conducts a mission or any other application. And publishing those models allows you to share the expertise, share the data in a very cost-effective manner across the entire enterprise. And it's through the ERDAS Imagine and ERDAS Apollo technologies that we can bring these capabilities to market more completely, more powerfully than any other company can provide. There was an article recently in the New Yorker magazine, May 6th, called the El Dorado Machine. And it was a very interesting article, an example of how LiDAR is being used to collect information over Honduras and Nicaragua in very dense rainforest areas, looking for lost cities, lost archaeological finds. And that's available online through the New Yorker website. If you hadn't had a chance to see that previously, one of the most powerful takeaways that was mentioned is that as the local governments and some of the industries are clear-cutting and burning some of these forested areas, they're exposing some of the archaeological digs, and then destruction and looting can then occur. So in those cases, the digital information that's been collected, those LiDAR data sets, in some cases may be the only evidence remaining of some of those lost civilizations. And that underscores the importance of this very powerful type of data and the ability to process and work with it in a very complete manner. So we do have a few minutes for questions, and we do have quite a bit that have come through the Q&A tab, so I'm going to expand this and pull off a couple that we have time for. First question, Steve, and I'm going to let you handle these since you're the technology expert. Typically, how long does it take to RGB encode a LiDAR data set?
Okay, so that's kind of a, how long is a piece of string kind of question. It obviously depends on the size of the data set and the type of machine that you've got and so on. But what I can say is Imagine has a very powerful capability to batch process. So all of these file-to-file type operations like RGB encoding or classification or filtering of LiDAR data sets, we can put into our batch queue, which then allows you to run, and typically, as I mentioned before, LiDAR is because it's so large, your data provider often delivers LiDAR data set as a bunch of tiles. So you might have 5,000 tiles of LiDAR data covering your area of interest. And what you can do is actually just put all 5,000 in a queue, push go, and depending on what licenses of ERDAS Imagine you have, you can actually process 20, 30, 40, 50 or more processes at the same time, either using Condor, which is a free distributed computing software, or you can just use the ERDAS engines and distribute it among the cores of your own standalone machine. So I hope that answers the question.
All right, great. Next question, is the LiDAR toolset you demonstrated an add-on module?
Okay, so what we've done is we've decided to make the LiDAR capabilities Imagine just part of core Imagine. So most of what you can do is all the visualization stuff, all the measurement is available at the Essentials level. All the editing, file-to-file stuff is available at the Advantage level. And the only thing that you have to get professional for is classification. So it's all included in ERDAS Imagine. If you have your maintenance and you've got an Imagine license, you've got access to all of our LiDAR tools. No add-on module required.
Okay. Next question, looks like we have time for maybe one more. Can you please elaborate on how you filtered out vegetation from the point cloud in the Yosemite example?
Okay, so what we do is, let me bring this up. We have a, open a point cloud. Up here we've got a data set called Classify, and Classify will look at the points, decide whether that point belongs to a tree or a building or bare ground or water or so on. And then we've got another set of tools here called Filter, and we can actually go into the filter operation and say, just produce me a new file that's only bare ground points. All the ones that were classified as bare ground are now are created into a new file. So we can actually do that on the fly. For example, if we look at I don't know if I have. So these are all first return data sets, but if I've got classification, I don't think I did a classification of this. Oh, maybe I did. I can switch off the ground points and so on. So I can do that on the fly for visualization purposes, but if I actually want to create a new file, I can go through the process. And I'll let you in on a little secret. For the 2014 version of Imagine, which is coming out at the end of this year, we'll be able to do all of those processes in the modeler. So I can actually feed a LiDAR file in, do an RGB classification or an RGB encoding, classify that, run it through a filter, do a bare earth, change that into a raster, do a slope analysis on it, and feed it into a long chain of processes.
Excellent. Thanks, Steve. Well, it looks like we're at the bottom of the hour, and as Aaron mentioned at the top of the call, we'll be sure to go through these questions and provide answers back to the participants.
Okay. I wanted to thank all of the participants as well as Rob and Steve for being with us today. We hope our webcast has been helpful. Again, as Rob said, if you have any further questions, please feel free to contact Lacey Ween with Intergraph Government Solutions team at Carahsoft. Thanks again, everyone, and have a great day.
Thanks.
Thank you. Bye.